Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is FEA troubleshooting and optimization in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So as far as the content over the next hour today, I want to preface that I hope today's presentation will be useful despite any FEA program that you're using. So even if you're not utilizing RFEM, I believe that today's experience and troubleshooting and optimization can also be taken to these other programs. We'll definitely be working with quite a few simple models today, and I thought this was best to explain these concepts rather than overcomplicating with larger structures. So to begin, we'll be looking at model instabilities, which I know this is an incredibly frustrating topic, again, no matter which software you're in. So hopefully we can see today some tools to overcome these type of instabilities. And we'll definitely be working with our add-on module RF stability. This will help us with general stability and buckling analysis to overcome instabilities as well. Then we'll move on to a common question that many users have. Well, what is the right size for the FE mesh for my model? So we'll take a look at troubleshooting FE mesh size as well as optimization. From here, we can move into singularities, and singularities occur high peak stresses or internal forces that we know happen with FEA software, but in reality are not going to occur out in the field. So how can we overcome those within our program? Then moving on to member eccentricities or offsets. So the advantages and disadvantages of including these in our FEA software. And finally, looking at nonlinear features for improved results, and in particular today we'll be looking at line releases. So again, hopefully throughout all of these examples today, you'll be able to pick up on FEA tips and suggestions, not only for our program RFEM, but for any FEA analysis. So with that said, we can begin within RFEM today. So again, as I mentioned, we have pretty simple structure here. If I take a look at my cross sections that are defined, I can expand this within my project navigator. We have some beams that are defined with W6x12s. We also have columns that are defined by W6x20. You'll see down here at the bottom, we have these nodal supports. So these pin type support are defined here within this dialog box. And you can see we have 6 degrees of freedom, 3 in translation, 3 in rotation. Now notice for this pin support, I restrained the translation according to the global X, Y, and Z axes, which we can see these axes here. But I've also restrained the rotation about the global Z axis. So this just doesn't allow that column to freely rotate about its own axes for torsion, for example. So we restrain that here as well. Now, when I look at my beams at the top here, and you'll notice that these are just typical beam type structures, but they are defined with a member hinge. So as you'll notice here, I have released the rotation about the local Y and Z axes, and this is denoted by lowercase here, X, Y, and Z, and we can relate it to this picture. But I have not released rotation about that local X axis. So again, that's going to prevent this member from freely rotating about its own axis with this pin member end release. Taking a look at our simple loads that we've applied, distributed loads up here on my front and rear beam, and then a couple of point loads to essentially apply a lateral load to this structure. So this is under a particular load case here, and when we go to run this load case according to just a simple linear analysis, we're presented here with our first instability. And I'd like to encourage you that when instabilities occur, especially within RFEM, is to really read this text that's given to you here. We really do our best just to try and point you to the direction here that the instability can be resolved. So when we read this, we see that the structure is unstable. The instability is found in FE mesh node number 12. And if I drag this down, we can see that red arrow kind of pointing to where that instability could potentially occur. Now, not always will this red arrow be helpful in troubleshooting exactly where the issue is, but often it can be used. And the instability is occurring in direction phi z. So this is rotation about my global z axis. So I can close out of this dialog box, and we might be thinking, okay, well, we've restrained these pinned supports down here to restrain the rotation about the global z-axis, so that couldn't be an issue. My member end releases are defined okay. So we might be thinking to ourselves, okay, well, maybe there's a modeling issue. Well, under tools, we can go to model check, and you'll notice we have a few features here to help us kind of troubleshoot potential modeling issues such as identical nodes, overlapping members. If we take a look at identical nodes, we can set a tolerance and the program will actually list the groups of identical nodes here. But you can see for today's example, that's really not an issue. So if I've exhausted all of my possibilities trying to troubleshoot just graphically looking at the model, this is where we want to utilize our add-on module RF stability. So over in the left, the project navigator, I can launch this add-on module. And what this allows me to do is to run a general eigenvalue analysis on this structure for general stability design. And I'm going to specify the lowest number of eigenvalues 4. That's just the default. Now, the eigenvalue analysis is linear by default, but we also can run a nonlinear analysis if we choose to. But here's the problem. When we try and import the axial forces here from load case number 1, and we click calculate, the program gives us a warning here saying that the results are not available. And the reason why is because we cannot run a general static analysis in RFEM with this load case. So there's no way that we can run an eigenvalue analysis here. Well, this is where we would want to activate this checkbox down at the bottom where we can determine the eigenvector for an unstable model so the cause of the instability can be checked graphically. And notice this is now grayed out. We're not utilizing this load case or combination. So now when I click calculate, what you'll see here is we're presented with these results table, eigenvectors by node and eigenvectors by member. But really what's most helpful is if we just immediately jump to the graphics view. And these are going to be my results from RF stability, running that unstable model. Maybe I turn this to wireframe view here. And when I rotate the model around, I think we can clearly see what the issue is. And I can even show animation here of RF stability. We see that this member is not connected to the rest of the structure, so it's free to move about that global z-axis. So what we'll do is to turn off the results here. And if we zoom in quite a bit, well, sure enough, these two nodes aren't connected. And we might be asking ourselves, well, what point is the program going to automatically mesh these two node points together? And that does exist within the model. Under Calculate FE Mesh Settings, there's an epsilon value here. And this epsilon value, if we go to the full precision, is set at something pretty small, 0.003 feet. So this is the default setting, and you certainly can increase this, but you really need to be careful because if you set this to something too big, you're going to begin to merge nodes together during the calculation that really aren't meant to be merged. So we'll leave this as default because clearly this distance is much greater than 0.003 feet, and all we need to do here is just to grab this node and snap it to that column. Okay, so hopefully we've alleviated this instability. What we would do now is jump back to load case 1, remember with those same applied loads, and we'll begin to run the calculation. So I run the calculation, and sure enough, I have another instability. And now the instability is found in FE mesh node number 83, and I can see the red arrow pointing here. So this might be a situation where, okay, this arrow's along the member length, not really much that can be going on there. So maybe it's not so helpful in this situation, but it is in the direction Y. That's the error message that's given to us. So the translation direction Y. So again, I've troubleshooted this model looking at it graphically. I don't know the reason of this instability. So we jump back to RF stability. And once again, we have to keep this option checked because we are not able to solve this simple load case back in RFEM. So we calculate it again here, just like what we previously saw with that unconnected node. We take a look at our graphics, and realistically, we can see what the issue is here. We have all of these nodal pin support defined down here at the bottom. We have the moment release for our two beams at the top. So we have all these pin connections, but we have no lateral stability to this structure. So you can see RF stability is telling us, well, clearly the entire structure is going to fail. We apply this lateral load, it's just really going to hinge to the right side here. So how do we alleviate this? Well, we would just need to add in some lateral bracing. So we can go in to draw a new single member, and we access our cross-section library, and we'll choose a single angle here. Now, utilizing my filters on the left, we can choose a single angle of 3.5 by 3.5 by 3/8 from the AISC. Maybe we want to create a new material here, so we access our material library. Again, utilizing the filters on the left, we can choose steel A36 from the AISC standard. I click OK. And the member type here would be set to tension only. So the benefit of this tension only member is that when this member experiences compression, it will be completely taken out of the model. But in a subsequent iteration, if tension is reintroduced into the member, it will be reactivated. And this is because RFEM is a nonlinear analysis program, so it can activate and deactivate this member all within the same calculation. So I click OK, and what I'd like to do here is snap from the bottom point to the top point here. And now our hope is that we go back to this load case and we once again try to run the calculation, and sure enough, we are presented here with our results. So hopefully some troubleshooting here on just basic instabilities, utilizing that add-on module RF stability to help us. So going to our next structure here, an example, definitely a more complex system. And this is a previous structure I took from a webinar. So this was, if I change the display here, it will be quite clear, a timber structure, curved glulam members. I did the design according to the NDS standard. So you can certainly refer to our website or YouTube channel if you're interested in more of this. But as we can see, typical glulam beam members here, and if I change my view here to the member type, I've defined truss elements in between these larger beams, and the truss just means that we're going to apply a moment end release at either end here. Then I have some tension only members defined here with my X bracing, and these are just going to be cable elements. Then of course at the front and rear of the structure, we just have these small columns defined here. So looking at my load cases, I have a dead load applied here. So you can see uniform load applied across the top of my members. We have point loads applied to the top of the columns, and we also have a pre-stress applied to these cable elements. Looking at my next load case, we have a balanced snow load according to the ASCE 7, and then load case number 3, an unbalanced snow load. Well, when I combine all of these into my load combination, you can see here load combination number 2. It's combining those dead loads along with the balanced snow load. And I'd like to run this calculation here. So we will run the calculation. I click OK. And the program will run through this nonlinear analysis, and we are presented with yet again another instability. But notice that my text looks a little bit different this time. It says the model's unstable. The instability is found in FE mesh node number 94, so we can see exactly where that's pointing to. But this time the program tells me, yes, it's in the direction phi x, so rotation about the global x-axis, but the specified load is greater than the critical load. It goes on to tell us utilize RF stability to help you troubleshoot here. So how would I approach this? Well, when we're seeing issues related to critical loads, the first thing to do is to jump up to our load combinations. And by default, all load combinations are run according to a second order analysis. Well, let's just change this to a first order analysis, and we will click OK here, and let's try and rerun the calculation. Now, I will say if you cannot run according to a first order analysis, the first thing we should be thinking is we probably have a modeling mistake somewhere. But in this instance, the program runs okay. And the other thing to check is, do we have any crazy deflections? If you see things just flying off the page, well, you know that there's probably, again, some type of modeling error when the deflection according to a first order analysis is pretty large. But in our case, if I decrease this deformation factor and I look at our total, 0.4 inches. So really nothing too wild going on here. So why can we not solve according to a second order analysis? Well, this is where we would jump to RF stability once again. Now, the difference here is that I no longer need to utilize this checkbox down here, but rather I can select load combination 2 here from my dropdown, because remember, we were able to get it to solve in RFEM. And this is according to a first order analysis here, what I'm selecting from this dropdown. So we run a linear eigenvalue analysis. And what will be presented here is our critical load factors for our 4 different buckling modes. Now, looking at dragging this down, taking a look at my 4 different eigenvalues, I think we can see clearly here what the issue is. It's these slender columns at the front and at the rear of the structure. So when I look at this table and specifically at this value, critical load factor 0.565, what does this mean? Well, this is the factor that I can multiply my loads from load combination 2 before I'm going to see a buckling shape such as this. Well, anything below 1.0 is a big problem. The programs tell me I can only apply 56.5% of my loads from load combination 2 before my structure is going to fail. So how do we remedy this? Well, we can jump to our graphics view, and if we're curious here just to see those different buckling mode shapes in a little bit more detail, we can do so within our color panel over here. So I'm going to go back to the project navigator under my data tab and to take a look at my cross sections. And my slender columns here are very slender. I can double click on them and you can see they're only 3.5 inches by 3.5 inches. So maybe we edit this and instead we're going to use 5 inches by 5 inches. Same material. I don't need to make any modifications there. So now we're going to see slightly higher stiffness here with these increased member sizes. So then what we'd like to do is to go back to our load combinations here. Load combination number 2, we change this back to a second order analysis because the hope is that this now solves according to not only a first order analysis, but a second order analysis. And sure enough, we are able to get results here, and we can see that our total deformation is only 0.4 inches. So everything looks pretty good there. And we might be curious to see, well, what does RF stability look like once we've increased these member sizes? Well, we're still importing load combination number 2, but remember now this is according to a second order analysis, but that's fine because it solves back in RFEM. And here we're presented with critical load factors of 2.2. So it looks like we still, our initial buckling mode shapes here for this structure would still be related to these slender columns, but now the structure can handle 220% of the loads from load combination 2 before we're going to see any type of failure behavior related to buckling such as this. So again, incredibly useful to utilize this add-on module RF stability here. Okay, so jumping to the last instability example, you can see that the first 2 examples are related to members and 1D elements such as beams, columns, and so on. But instabilities can also happen with surfaces. So once again, this was a previous model I took from a 2-part webinar series on a little bit more information on plate and shell modeling within RFEM. And we have a typical tank type structure here. So when I take a look at my applied loads, we have our first load case, which is just self-weight, so no additional loads are shown here. Then we have our fill load. So this is going to be an internal load kind of pushing out on the structure walls here. And we have a wind load, which includes an uplift from the bottom and also a lateral load coming from the left with a suction force over on the right-hand side. So taking a look at my load combination where I've applied all three of these load cases together, we'd like to begin our first analysis. So I'm going to start the calculation here, and similar to what we've seen previously, we get an instability. So once again, let's try and read this information here to give us more information about what could possibly be going on. So we have an instability in FE mesh node 2371. So I look at here, okay, well, it looks to be at the top of this leg, the bottom of the actual body of the tank. This time it's in the direction Z. So we'll have to look into that a little bit further, but we still get that same error that the specified load is greater than the critical load. So once again, I'm going to take the exact same process that we just saw for our member elements, but it also can be applied to surfaces. So we go in here to our load cases and combinations. And under calculation parameters, instead of running according to a second order analysis, we change this to a first order analysis. And it's our hope now that we're able to see the calculation run. And again, if we're not able to, then let's begin checking for duplicate members, duplicate nodes, unconnected nodes. You know, maybe we have the wrong units defined for our loads. So many different scenarios here. But in this particular case, the model solves great for a first order analysis. If I decrease this deformation here, we see the total deformation is only 0.05 inches. So relatively nothing going on here. So we go back to our trusted RF stability, and we are going to import in load combination number 1, because remember, we do have the ability to solve for that back in RFEM, so we do not need to utilize this option down here at the bottom. We click calculate here, and notice this will take a split second longer than what we saw with our members because we've introduced many more FE mesh points into the model than what we previously had with the members. But eventually we are going to be presented with our results here, including the critical load factor. So when I kind of move this down here, I think it's maybe quite apparent what exactly the issue is. It looks to be buckling of these leg elements here. And again, we're seeing values less than 1.0. So the program's telling us we can only apply 67% of the loads from load combination 1 before we're going to see a failure such as this one. So going back to the graphics view here, maybe we turn this to wireframe view to view this in a little bit more detail and more clearly. Again, we can scroll through to these different mode shapes here. And again, they're all related to this leg element here. So what I can do is to highlight all of these elements, and I can right click to edit the surface, and we'll notice that our thickness is only 0.04 inches. So this is probably not sufficient in this case. We definitely need to increase this. So let us try 0.14 inches instead. I click OK. So again, we jump back to our load combination and we change that load combination back to a second order analysis, because once again, it's our hope that this model will not only solve for first order, but of course will solve for second order. And sure enough, we're here presented with our results now. So just by increasing the thickness of those legs, we've kind of alleviated the buckling issues that were taking place. So again, just RF stability can be used not only for member elements, but really we can troubleshoot the stability of surface elements as well. All right, so we will move on to the next topic. So that's quite a bit with instabilities, but hopefully you can learn something here. Definitely take a look at the text that's given in the error message and utilizing RF stability to overcome those issues. So I mentioned in the PowerPoint a very common question. What size should my FE mesh be for my surface elements in order to give me accurate results? And that's always a good question, and it's not so easy just to answer for every single model because this really depends. So you'll notice here that I have 5 different surfaces, and they're actually all identical. If I double click on one of these, it's just a steel A36 material, 2 inches thick. If we take a look at our support conditions, we have line supports defined on either side, pin type support, restraint with translation on one side, and then we have a roller type support on the other. Taking a look at our applied loads for this initial load case, just a 0.1 distributed load here, 0.1 kips per square foot on every surface. So if we turn this to wireframe view, let's begin with our global FE mesh settings. So under calculate FE mesh settings, we can set this global mesh here, and you can see I've set mine to 5 feet. So when I click regenerate FE mesh, I click OK. Let's take a look at our first surface here. So this is going to abide by that global FE mesh of 5 feet. And you'll notice a very coarse mesh. We only have 2 elements across the width. And I can tell you this is definitely not ideal. The only place that we're getting results here within the program after we run the analysis is at every FE mesh point. Definitely not adequate, much too coarse. So as we begin to move on down the line here, you'll notice that I've added these FE mesh refinements, and you can add an FE mesh refinement about any element by just highlighting it, right clicking, and you'll see here FE mesh refinement. And in this case, I went ahead and set the FE mesh refinement to 2.5 feet. So about half of what we're seeing from this adjacent surface. Well, I continue to do so by adding in an additional FE mesh refinement here of 1 foot. Well, my fourth surface here has an even smaller FE mesh refinement, 0.25, so about 3 inches. And finally, we have this very refined FE mesh at 0.1 feet, so a little over 1 inch. So it might be interesting for us to compare results then for these distributed loads. So we're going to run the analysis here. And let's take a look at, I'll turn off my sections here, the initial deformation. So just primarily looking at it, nothing too drastically different here. I'm sure we would get some different values. But I think the biggest telling difference here is to take a look at the internal forces. And let's begin with our MY forces. So I've set my contours here according to every FE element, and you can see that bending along the local y-axis of the surface, so this is in the length direction, is drastically different when we compare it as we move down this line here. So as you can see, and I've already mentioned, this coarse mesh, much too big. We're not going to gain accurate results here. When we take a look at the MY forces, same concept. Comparison of this first surface versus these last couple is very different. Now we can compare here section cuts as well. So what I've done, and I'll turn on these sections and I'll turn off my ISO band so this is a little bit easier for you guys to see, is I just made this cut right down the center of these surfaces. And under my display tab, let me also turn on how those cuts were made. So I'm currently looking at the MY force, so again along the length, and you can see again how the diagram here of this section cut changes. And we're definitely getting a much more realistic view when we move into these more coarse meshes. The other thing to pay attention to are the values. So the max value here moves from 4.583, 4.5856, 4.932, but then we're getting into 4.945. 4.946. So at some point, our cost to benefit ratio, I guess, so to speak, that where we're continually refining this FE mesh is really not drastically influencing our results. So for example, these 2 elements here, this has about 1/3 the FE mesh, the one on the left than it does on the right, but yet our results are only changing by 0.001. So it's kind of this happy medium here to find out the right balance of when we are able to refine our FE mesh to gain accurate results, but not too much so that our calculation time is increasing significantly because we've added all these additional elements. Now we can also view the same concept with our MX forces, and I will turn on here my diagrams in the other direction of my section cuts through the surface. Same thing. You can see that this diagram here is definitely not what we'd like to see, but as we begin to move down the line, we're seeing a little bit more realistic behavior here. But again, take a look at the max bending forces, 0.479 kip feet, 0.472, 0.47. So very little difference when we're looking at some of these surfaces towards the end here with an increase in FE mesh. So I would argue that maybe the second to the last, or possibly even the third to the last, just depending on your structure, is adequate for gaining those accurate results while not waiting forever for your solution to run. Now, how do we kind of check this for our own structure? Well, we can just manually refine the mesh, run the calculation, take a look at our results. Let's rerun the calculation with a more refined mesh. Are our results drastically changing? Yes. Well, then we need to continue refining until we get to a point where the results are not changing much, and then we can probably move forward with our static analysis. So to put this practice into a real life structure, we'll jump to our next example here. And this is the FEA model of a connection. So we have a beam splice here with two HSS members, and this is utilizing a contact solid here. And a contact solid is just going to allow these two plates to fail in tension where the bolts will take over, but yet in compression we'll see full force transmission. But definitely a much smaller scale here in terms of our FE mesh. So turning this to wireframe view, if we go to calculate FE mesh settings, typically for a new model, the default mesh size is 1 foot or 12 inches. So if we were to move forward with this 12 inches and we regenerate our FE mesh here, I think we can see that this is absolutely not correct. There's some portions of this HSS sidewall that don't even have a single FE mesh point across the width. So this is definitely telling us that we really need to refine this FE mesh to get multiple elements across this width here in order to get accurate results. So under calculate FE mesh settings, let's change this instead to 1 inch and we'll regenerate the FE mesh, and I click OK. So now you can see that this looks incredibly better. Now, the program is still intelligent enough, and you saw this in what was just shown with the 1 foot mesh, that it will still tie together the nodes and the line elements despite the large FE mesh. So we don't need to take care of any of that manually, but we definitely needed to refine the FE mesh for the surfaces out here. Now, there may be situations where we want to further refine the FE mesh, and again, we can utilize those FE mesh refinements. So we just right click on this line element, we can add that FE mesh refinement here. So you can manually do that. Now, there is a helpful tool within the program that essentially will do all of this manual work for us when it comes to the FE mesh. So under under calculate FE mesh settings, you'll see here adaptive mesh refinement. Well, what does this tool do? We can turn it on here and we can select any load case or combination that we'd like from our dropdown. Now in my case, I only have one load case defined. We say here an average error tolerance, which I'll just leave this at 0.1%. The program will start with a pretty coarse mesh, as you can see over here on the right. It will go ahead and run the analysis, then it will refine the FE mesh, and it will compare the results from the previous iteration. Well, it can continue to do this until we're not seeing the results change within 0.1%. So it's actually doing what I just told you to do with the previous example, to do that manual refinement, take a look at your results. This will do it automatically for us. So when I click OK and I click calculate, generate FE mesh, it looks like it's almost running a calculation, but it's actually determining the FE mesh for us. So once this is done calculating, what will be presented here is the refined FE mesh. So you can see that larger FE mesh at some of these HSS surfaces, but when it comes to the plate around our bolt openings, or maybe these curved portions where we're getting closer to our line support here, we're going to see a more refined mesh. So this is going to be the ideal mesh to continue moving forward with our static analysis. So again, you can either manually set that global mesh and add in your own FE mesh refinements if you'd like a little bit more control over it, or you can utilize this adaptive mesh refinement within the program to have the automatic mesh set for you. All right, so this will bring us into our next topic, also related to surfaces and somewhat related to FE mesh as well. We'll move on to singularities. And singularities are something that really happens in every FEA program. We experiencing these high peak stresses and internal forces that really just aren't going to occur in real life, but they're inevitable in FEA software. So this will be a good example of why they occur. When we look at this concrete structure here, on a much larger scale, we have a 2D surface for our slab. So this is going to be 4,000 PSI concrete, and the thickness is set at 10 inches. Well, we also have these columns framing into this slab from underneath it, and these columns are 15 inches by 15 inches. But the problem is when we turn this to wireframe view, and again, this is the case with any FEA software, that members are represented by this one-dimensional element. And it's framing into this two-dimensional surface at this single point here. So all of the force transfer is taking place at this single FE mesh point, and this is a result of why we get singularities where we don't have really load distribution. So you can see for this example, what I've done is I've applied a couple gravity loads here for dead load and live load. And if we run the analysis, which I've already done in this case, and we take a look at our results, we'll turn on our ISO bands, turn off our loads. Well, okay, the initial deflection, nothing too strange here. But let's take a look at the internal forces for our slab element. And so we'll turn this on and we'll take a look at MX. Well, initially looking, MX looks okay. Obviously we're seeing some positive bending moment in between these column supports. But then there's the case here over the columns where we're seeing extremely high negative bending moments. And of course, there will still be some negative bending, but these look to be pretty high at these locations. MY, same concept, positive bending in between where these columns are spanning, but then very high negative bending moments where it frames into these single 1D member elements. And even more so can be said about the shear forces. Now, we fully expect shear forces to be higher at these column locations, but I've also made a section cut through my structure here that I'll go ahead and turn on, and maybe I turn off my ISO bands. And if we look at this section cut, you'll see that these shear forces are very high. We're seeing from negative 66 kips clear up to 163 kips, all at this single point location. So there's got to be a better way to kind of distribute the forces over that entire portion where the column's framing in, because we know in real life it's not represented by this single line element. Well, this is where we'd like to add what's called an average region. So under the project navigator, we can find average regions listed here. And I can right click and I can choose new average region. And it's exactly as it sounds. We're going to average out the internal forces over a set width and length. And then this will be presented to us so that we can overcome these high singularity forces. And actually, one other thing I forgot before I do this, let's jump into this in just a minute. I also wanted to preface that before you place in those average regions, let's think about the FE mesh. What I'd also like to do here is to refine the FE mesh around these singularity locations. I think it's best to kind of isolate these high peak forces into an even smaller area. And we do so with an FE mesh refinement. So we can right click on that node, add in that new FE mesh refinement here by creating a new refinement type. But remember, we can also utilize under calculate, FE mesh settings, this adaptive mesh refinement once again. So just to get the ideal mesh refinement. But in this case, I'm going to set the value here to something much lower, this percentage. And I need to do so in order to see some refinements about these columns and such. So under calculate, generate FE mesh. Let's take a look here. Here's the initial coarse mesh in the background, and eventually we have these nice FE mesh refinements here, especially around our reentrant corners and our columns. So let's rerun this calculation. I just want to show you that actually what we'll see here is those high peak stresses and internal forces are even higher. We're up to almost 770 kips. So that is also what's going to happen when we refine the FE mesh. We continue refining more and more and more. We're just going to see those internal forces and those peaks go up more and more and more. But that's okay. The whole intent was to kind of isolate that to a smaller area here, because now let's jump back to the average region. And we right click on the average region to create a new definition type. So as I was saying, exactly as it sounds, it's going to average out these internal forces over a set dimension. Now we can choose here the surface we'd like to apply it to. So it'll just be surface number 1. So only one surface here. I'm going to place the average region at the top of this column. So I graphically selected it. We choose the shape. So it can be a rectangle here. We choose the dimensions. Now, we might be asking ourselves, well, what's the correct dimension for an average region? And this all depends on your model. It's definitely up to the user's discretion on how big to set this average region. Now, in my case, I'm going to set this to 1.5 feet by 1.5 feet. If you set it to something too big, we might not be conservatively designing this location around this column. You set it to something too small, maybe we're not alleviating the singularity. So we also check all 4 of these options here. This just means it's going to average out the internal forces in all 4 directions. So now when I click OK, you'll notice that immediately that high peak force is gone because we're averaging it out over this entire area shown with that blue symbol. I can take this average region, hold down my control key, drag and drop it to my next column location. You'll notice that peak's now gone. Let's continue to do so with this third column. And now we're seeing those high peak stresses are eliminated. Now, not entirely, because we do want to see some shear, of course, at these locations. If we right click along this section cut to view our results diagram, this is just going to give us a little bit more detail along the length here. I'm going to turn on MX, MY, VX, VY, and we can clearly see where that average region was applied. You can see it's flattened out here along these internal force diagrams. So average regions can definitely be helpful in overcoming these singularities. They can also be applied in the design add-on modules such as RF concrete surfaces, where we design the reinforcement for this element here. Well, these average regions can also be considered directly within the add-on modules. So moving on to our next example, also to deal with singularities, there are situations where maybe average regions don't help in certain scenarios. So for this particular case, we have here just, let's say, some type of shear wall or gravity loading wall, and we have 4,000 psi concrete 6 inches thick, and you can see just a simple gravity load applied. The top here is a distributed load. And I've also applied a couple columns framing into the bottom. Now these columns are quite compact, we'll say in one direction, 2 feet by 6 inches. But regardless of the dimensions of this column, when we turn this to wireframe view, we'll still see that these members are represented by these single line elements framing into this one tiny FE mesh point here. So when we take a look at the results from this first load type here, and we're currently viewing the deformations, we zoom in here to look at our deformations. Well, this definitely is not ideal. We know that this column has a pretty wide width of almost 2 feet, so we wouldn't expect deflection such as this. Well, then if we take a look at our internal forces, and let's take a look at NY forces, this is going to be compression and tension in this wall. We have extremely high peak forces here, you know, those singularities. We're seeing compression here at 454 kips. So this is definitely not ideal. So how can we see better load distribution over this area? And this would be a situation where I'd say, you know, average regions could be helpful, but I think there's a better approach here. And that'd be to apply a rigid element for load distribution. So we'll go into draw a new member. Now, under the member type, this is where we're going to choose rigid. And a rigid element, you'll notice you can't choose a cross section or material because it's just going to be a very, very high stiffness element. So what we'll do here with this rigid member is click OK. It's asking me to clear my results. I'm going to zoom in here, and I am going to snap from the top of my column 1 foot to the left, and I'm going to snap from the center of the column 1 foot to the right. So there's that rigid element. This is going to represent the full 2 foot width of that column. Remember, if we turn this to a rendered view, this is kind of what we're helping here with the load distribution. I'm going to take these 2 rigid elements. I hold down my control key. After they are selected, I can drag and drop and copy them to the other side. So let us rerun this same calculation just to see how our results will vary. And when we take a look at our global deformations, this is definitely something that looks much better. We kind of have a straight deformation line here at the top of the column due to those rigid links, but yet we're going to see, you know, downward deflection here spanning between the columns. And let us jump back to our internal forces, and in particular, those tension and compression forces. So you can see now we're seeing high tension forces, or sorry, we're going to see, high tension forces at the bottom here. We're going to see some compression forces more towards the top. And this is exactly what we'd expect. So previously, we had those singularity points that were kind of overtaking all of the internal forces here. Now, we might still have a slight singularity here where this rigid link is ending, and this could be where we use an average region to maybe help distribute that load a little bit further. But all in all, this is going to give us much better results than what we saw previously without those rigid elements. Okay, so moving on to our second to last topic, I want to take a look at here. We will take a look at eccentricities, and we'll jump to this model here. Very simple application. Simply supported members here, but I want to take a little bit of time to discuss member eccentricities, member offsets, because this is a topic that comes up over and over again. So it must be remembered that finite element analysis software is not a BIM software. So BIM, you know, we're using to ultimately create these drawings to maybe give to the contractor to show exactly how members are framing into each other. But when we're talking about the finite element analysis software, this is truly is what it sounds. It's for the analysis, for the engineer. So it's not our goal to make sure that every element is lining up perfectly with every other adjacent element. Now, so I'd like to, you know, take a minute to talk about when eccentricities can be helpful, but also when they can really cause unwanted behavior within the program. So starting off with the simple application here, distributed load over these simply supported members. You'll notice that first element here, I turn this to wireframe view. Everything's just framing into it at the center line. Well, the second element here, and let me turn off my nodal supports. What you'll see is that I've actually added in an eccentricity so that under the Options tab, I manually set this to drop the top of steel to where that nodal support is. And I manually set that here in the global Z direction. So what you'll notice when I turn this into wireframe view is that we have these rigid elements here that we've kind of dropped this down at those nodal supports. Now, we're not truly adding in rigid links along the member length. It's actually taken into account with the stiffness matrix, but just an easy way to think of it is to imagine these rigid elements, dropping this member down all along the length. So we might think that that's harmless, and we go to run our analysis here, both with the same distributed loads. And I'd like to take a look at the results. And we'll immediately start off with the moment diagram. So a simply supported beam, we take a look at our first example here. This is exactly as we'd expect for our moment diagram, peak moment right here at the center. But as we transition into those nodal supports, which are pin roller type situation, we expect no moment. Well, by introducing this eccentricity here to drop the top of steel down to where our nodal support is, we now have a negative bending moment here due to those rigid elements at the end. Our peak moment here in the center is almost half of what we're seeing here with our original beam element. So definitely not ideal when, again, we're looking at this render view to drop that element down here, because we're going to get these unwanted moments at the ends. We're not getting the full moment here at the midspan. So this is definitely a scenario where you really need to think to yourself, okay, why am I dropping this element down with this eccentricity? Is it really necessary with this finite element software? So moving on to our next example right next to it, we'll go ahead and take a look at a different type of system. So this is just going to be a simple 2D frame here, and you can see I've restrained the top here out of plane. Chevron bracing here with some single angles. Turning this to a wireframe view, my first example, everything's framing in nicely at the center lines just by default. Well, when I take a look at my example here in front of it, what I've done is I said to myself, and I'll turn off those nodal supports here, I want to drop the top of this member down to the top of the column. So we've added in that eccentricity here, and I did so, which you can see under my eccentricity options. I took advantage of this relative offset. I took the top of the member, I offset it from member number 15, which is the column. The advantage of using these relative offsets is that when the member size changes, if I needed to do so, the eccentricity is automatically updated, so I don't need to manually adjust those. But point being, we could have even taken this a step further to move the eccentricity from the axial offset here as well. But when we turn this to wireframe view, we can kind of see this member drop down below here again with those rigid type elements, again, being taken into consideration with the stiffness matrix. A lateral load applied here. So we run this analysis, and when we take a look at our results, pretty much everything looks to be fairly the same. We're taking a look at our axial forces. Maybe we take a look at our shear forces as well. But taking a look at the bending moment, the strong axis bending moment, let me create a visibility for just these two upper beams here. Well, you'll notice the drastic difference with the strong axis bending. In my first example, we transition here from a positive moment, 0 moment at the midspan, into a negative moment. Quite a different story when we've taken into consideration that eccentricity. So we have a huge jump in the moment where those chevron braces are framing in. And we know that this really just is not ideal behavior. So this is definitely, again, a scenario where it must be considered, okay, do we really need to consider these member eccentricities and offsets, or is it doing us more harm than good? So moving on to our final example in this particular model. So we'll cancel our visibility mode. Let me once again turn on my nodal supports. We'll move over to the right here. Just a T-type frame. And with this system here, let's assume that we have these beams framing over the top of this column. And once again, my first example in wireframe view, everything's framing in at the center line here. So just default settings, no eccentricities. But when I look at my example here, what I've assumed is that, okay, well, if I know my beam is running along the top of this column, I'm going to offset this column so that it frames into the bottom of the member. And I did so under my eccentricity options here again. I use this option down at the bottom where I can apply an axial offset from the adjoining member. So I've applied that, and you can see here that we have a small little link that's going to drop that member down below. So let us once again take a look at the examples, and we'll turn this to wireframe view. Let's turn off our loads. Same loads apply to either scenario. And we take a look at the bending moment. Now, only 0.1 kip feet of difference here between my model on the left and my model here out in front on the right. When we take a look at shear, again, about 0.02 difference kips between the first and the second examples. Maybe we're interested in seeing our axial forces within this column. If we take a look at the axial force down at the bottom, 26.05 versus 26.01, so 0.04 kips of difference. So my point being here is that we perhaps have a huge model. We've applied all these eccentricities for our columns to drop that down, to the bottom of the beams framing up above it with absolutely, no influence or very, very little influence on our results that really don't make it worthwhile. So maybe not detrimental here in terms of additional forces, but really no difference. So there's no reason to apply these offsets in these situations. So again, this isn't a BIM software. We're just truly here to do the analysis. Now the exception, well, we'll get into another exception in just a minute, but considering connection design. Of course, with connection design, you need to consider offsets and eccentricities when, a beam is framing into the face of a column. That's clear. But when we're looking at overall member design, in so many scenarios, it's just really not necessary. So jumping into an additional example here, we'll go to the second example. Now there are scenarios where we do need to consider eccentricities for the full structural system. And a perfect example of this is composite behavior. So you'll notice my initial example and system up here, I have a concrete deck. I have also my steel member, and everything just modeled with the center line. So I've applied that here. You can see those center lines just kind of lie directly within each other. Well, taking a look at this example down here, we have also that concrete deck, but I have applied this member eccentricity. So under my member options, I have offset the top of this member relative to the surface element in the bottom of the surface. So again, if my thickness of my deck changes, this eccentricity will automatically update. I don't have to manually go in here to make those changes. So that is definitely a benefit of using the relative offset. So with composite behavior and comparing one system here to the other, let's take a look at our results. So just a distributed load here, area load, looks like 2 kips per square foot. So we run our analysis and we take a look initially at our deflections. Well, the first thing to notice, and I can turn on here my sections, is that we have significantly greater deflection with this system here where the elements are modeled at their center line. So slightly less deflection here with the true offset of this member applied. Now, we know the entire purpose of composite behavior is so that the slab element is going to take the compression forces and the beam element is going to take the tension forces. So if we turn on our surfaces and we're going to activate here, let me set this back to default, the NY forces. So this would be the tension and compression forces along the length here in the Y direction of the surface. And maybe I create my user-defined visibility. There's absolutely no compression going on with this first example. Well, if we compare that here to our second example down here, and let's create a user-defined visibility. And let me set this back to default. You'll notice that we have significant compression, 80 kips here towards the midspan. Now, this transitions into some high tension forces, and I would say this could probably be attributed with a singularity. So we could probably use an average region, maybe rigid links to kind of take care of that. In our control panel, maybe we completely take out tension and we adjust this control panel here only to look at the compression forces. And it's really as we'd expect. We want this slab element to take those compression forces from this applied area load. Well, in turn, if we turn off our surfaces here, let's take a look at our members. And we're most interested in here, and let me cancel my visibility. Let me turn off my sections, is the axial force of the member. Well, looking at my system up here, I don't have a single axial load within this member at all. So it's not taking any of the tension. Well, I take a look at here, we have a very high tension force, 571 kips. So that's exactly the behavior we'd like to expect. So definitely scenarios where we would want to apply these member eccentricities and offsets. And one clear example of this is with composite behavior design. So let us jump to our last example today. And this will be somewhat related to this composite behavior. So this time we have a CLT deck. So this is cross-laminated timber. I've utilized my add-on module RF laminate to define those various layers within this floor. And below it, I have my glulam members, and I've applied this eccentricity because I do want this deck sitting on top of these glulam members. You can see on either end, I've also applied some member hinges. So I have released torsion on one side, and then I've released moment on both sides. And what you'll notice is that we ultimately are trying to gain composite behavior design between these two elements. We have the applied load here of 0.5 kips per square foot, and we run our analysis. So what we want to do is to quickly run this particular load case to take a look at our internal forces of our members. And when I take a look at torsion, for example, we're seeing here some pretty high torsion forces within the structure, and this definitely is not ideal. Typically, when we are connecting the CLT floor to the beams below it, we're going to use a screw type connection, and the screw is going to release the moment so that we're not so concerned with torsion in our members. The other thing is if we take a look at the bending moment, well, these are supposed to be simply supported member elements here with pin and releases, and we have extremely high negative bending at one end. Now it eventually goes back to 0, but we definitely don't want to see such high negative bending either. Well, the problem is that we have defined this composite type behavior and everything is rigidly connected, when in reality we want partially composite behavior because of the connection between the CLT floor and the glulam member. So how can we take that into consideration? Well, what we're going to utilize is what's called a line release. So over in my project navigator, I can right click here and I can choose new graphically. And the first thing to do is to define my line release type. And you'll see here we have 4 degrees of freedom. The first thing I'm going to do is completely release that rotation about the line's local x-axis. So it must be clear that these x, y, and z axes refer to the line element itself, not the member and not the surface, but I'm going to release that torsion along that line x-axis. Now in the translation directions x and y, let's assume we have some type of slip here for our screws connecting these two elements. So we would probably set this as something like 10 kip feet for our spring constant. So we still have some connection there, but it's partially fixed. And finally, in the vertical direction, I'm going to utilize a nonlinearity. I want this connection to be fully fixed if we have a downward shear in the local z direction of the line. But in the event that we have an upward force, a shear in the local z-axis, we're just going to add a small spring element here. So once we have created this line release type for all of these definitions between the member and the surface, I can click OK. I'm going to release surface number 1. When I click OK, I have the ability here just to highlight over the entire member. And what you'll see now is this symbol, which represents the line release, connecting all of these glulam members to my CLT panel. So I rerun this calculation, and hopefully we'll see a little bit of a difference here with our results. Now notice it's going to take just a split second longer because we've introduced this nonlinear behavior with these line releases. But we take a look at our torsion. Well, it might still look like we have some torsion, but these are pretty small values, 0.04, 0.1. This is much, much lower than what we were seeing before because we've now kind of released that behavior between those two elements. If we take a look at our strong axis bending, we're no longer seeing those high peak negative bending forces either, which is exactly as you'd expect here. We have positive bending for all of our member elements. So some of these nonlinear applications can further be used in the program to really get the desired behavior that we want. Okay, so that will conclude all of our examples today. And I know that was quite a bit of information. We went through many models. I just want to remind everyone that these webinars are recorded. So this will be up on our website, usually within the next day. And you can visit dlubal.com to rewatch it. You can download these same models and play around with it yourself. So definitely visit our website for more information, also on RFEM or RF stability or anything else that you may be interested in. I also want to let users know, especially if you're a new user, we have some upcoming online trainings. For example, next week we have a beginner timber training. So that might be interesting for you if you're wanting to learn more about the program for timber specific design. So if you have any questions about today's presentation or anything else, feel free to contact us in our Philadelphia office. And our email and phone are shown down at the bottom of the screen, info-us@dlubal.com. And again, you can reach us by phone at 267-702-2815. So we will have many more upcoming webinars. Try and do them about once a month. You can register on our website at dlubal.com under support and learning and webinars. As most of you know, I tend to send out a couple reminder emails through before the presentation will take place. So feel free to sign up through email as well. As far as PDH certificates, these will be automatically emailed to all participants. So as long as you are here for the full presentation, which is a requirement by the various states we are pre-approved providers, you will automatically be getting this PDH certificate sent to you. But please be patient. It's not sent automatically after the webinar ends. It will come usually within the next day or so. If there were any attendees today and you did not register for the webinar, but perhaps you watched with a colleague, make sure you request that PDH at info-us@dlubal.com. So again, if you did not sign up with your own email address and your own name, and you were here for the full 60 minutes, please request that PDH through the email address shown here. So as always, I want to thank everyone for attending today's webinar, and we hope to see you at our next one. Thanks. Bye.